Welcome, everyone. Thanks for joining today. I'm very happy to introduce Annegret Larsen today, who is joining us as an assistant professor in soil geography and landscape from Wageningen University. Annegret is specializing in human landscape interactions, ecosystem services, and rewilding. She is also contributing to bridging the gap between science and public and involved in citizen science initiatives, and also a member of the European Geoscience Union's policy working group. Additionally, she promotes the emerging field of biogeography, organized conference sessions and in workshops to advance its development. And with that, I would like to give you the stage, Annegret. I'm looking forward to your talk.
Thank you very much. And thank you very much to give me the opportunity to present my research today. So this is a little bit of this presentation is a little bit of a journey through my personal take on my personal career, how I've always wanted to investigate things. So it comes from different angles, but I'm going to do my best to put it all into 1 times 40 minutes, which is potentially a little bit of a challenge. But so what this is all about is about something that I call the dreams of natural streams. And what you can see here as a starter is a natural stream, right? And it is also considered a biodiversity hotspot because of this. However, there is hardly any river left within Europe that can be considered natural. And the mystery of finding out what is really natural is what has triggered me, or which has always fascinated me. So we all live, and I don't have to preach to the choir, in an age of dramatic biodiversity decline, which is currently not being halted or reversed by the conservation practices. And because of this, the United Nations have called for a decade of ecosystem restoration. And the European Union, I think very similar to what the Swiss government did too, finally came up with the new nature restoration law, which sets binding targets, very important. And for rivers and floodplains, this means, this is a law actually, that we are going to have to restore 25,000 kilometers of rivers by 2030. Well, this becomes increasingly unrealistic, but at one point in the future. And they actually say we have to restore those rivers to something that is natural. So, however, we don't know what is natural. Yeah. So, and this is what I'm going to talk about. In geomorphology, and that's what I'm originally. I'm a geomorphologist. There is something that is called a discussion about the dreams of natural streams. And this means that we have been doing river restoration for a very long time. Yeah. So, but we don't know what is successful and what's not. It's really hard to validate, right? It comes from different angles. And the argument behind this, it's a very influential paper by Dave Montgomery from 2003, I think already, is that we actually, all these restoration projects fail because they don't know what natural is. So we restore the rivers to an arbitrary state, which we call natural. And because of this, Dave Montgomery argues, we only dream about natural streams. We actually don't know. It's not evidence-based. Yeah. And as a fluvial geomorphologist, as I said, this is very logical to all the people that look into the geological records, because we see a dramatic change at one point in the stratigraphic profile of almost all rivers, right? And this is a transition from something that was there before, here with the question mark, into an anthropogenic state, which we understand very well and we've researched very well. So the reason why we actually don't really understand what was there before, like in the lower layer, like the darkish layer, is because in opposite to what controls a river in an anthropogenic state, it's controlled by ecosystem engineers, by nature, by the vegetation, by the ecosystem. But as we know very little about the local ecosystem that controlled that rivers in the past, we also hardly understand what the processes in the river was, right? But after that, in an anthropogenic state, we know very well, we know humans, we know archaeology, we know history, right? And we can reconstruct that much better. So for me, what that meant is that I I started investigating the current processes between biota and earth surface processes, the interactions between that. And then I wanted to know what the changes over time of all these ecosystem engineers and the vegetation that controls river processes are. And I want to apply this in terms of restoration. So unfortunately, we had, that's a little too fast, we had very little evidence on how vegetation has changed over time in those river catchments. However, there's a new tool developing, which is called sedimentary ancient DNA. And I'm going to present that at the end of the talk, okay, which will make us, hopefully in the future, be able to transfer the process-based approach in understanding the feedbacks and processes between biota and rivers, fluvial dynamics in the present. We can transfer that then potentially into the past by knowing the presence of past ecosystem engineers, and we can apply that then in restoration projects. So, but first, I would like to introduce you to one project that I had in the last 4 weeks, in which I tried to unravel, or we actually, it was an interdisciplinary team, we tried to unravel the feedbacks and processes between biota and river dynamics, and what would be a better animal, yeah, to do this with than the beaver. Yeah. So the beaver as the main ecosystem engineer, I didn't put a slide in to explain what it does. I think it's in this biodiversity setting here relatively clear. The beaver builds a dam, it creates its own niche, and hence is one of the best examples of an ecosystem engineer, right? Because it modifies its environment based on what it needs, basically. Yeah, and that environment is, so it modifies first the hydrology, yeah, so it builds a dam, okay, in the river, which you can see here, and that increases the water level upstream of the dam, and if the topography allows it, then the water flows on top of the floodplain, creates a swamp, a wetland, extensive wetland in the floodplains, and that then has all sorts of feedbacks also with infiltration and groundwater and all these sort of things. I'm going to talk about that a little bit later. So, in overall, what that means in terms of hydrology now, the beaver as an agent of hydrological change is that it changes the water balances. So it leads to an increase in storage of water. When it is able to build a dam, we can't forget, so it definitely leads due to the backwater effect of the dam that it builds within the river. It definitely leads to a surface water storage change, a positive storage change. But it also, due to the infiltration, leads to an increase in groundwater storage, shallow groundwater storage. But this is much harder to quantify. But it can play a very important role. Then what it does, mainly by actually increasing the residence time of the water within the pond, but also within the shallow groundwater table around the pond when it starts to flood, is that it leads to something that we call water purification. So through different pathways, it can actually alter the nutrient load in water, and we know that from the literature. Then, that is more what I'm very passionate about, is also that it changes the sediment flux. So overall, when it's allowed to build dams, and please understand, it hardly ever builds only one dam, right? The beaver always builds many dams. We call it a beaver reach. And this leads to a slowdown in overall sediment residence time. So the sediment needs much longer to pass the beaver reach, yeah? However, so it's also very important that because of all of these processes that I just very briefly discussed, that it is very dependent on the context. Yeah, so it's not going to have the same effect depending on where it is within. And now this is a very geomorphic perspective, of course, but where it sits within a catchment, right? When you think about going from upstream, so A would be Switzerland, yeah, very high up, then D is the Netherlands. Yeah? So, and when we look at this gradient, it's a landscape gradient from upstream to downstream, then the beaver is going to have different effects depending on where it builds the dam and where it modifies the stream. And it also cannot build everywhere dam, so it has also limitations to this. Yeah? And that's the next point. So in order to better understand that, what we first did was we modeled based on existing data from the Swiss government, so from the CSCF actually, we modeled the controls and extensions of beaver dams within Switzerland. Oops. So there are several biases. I'm not sure how much I have to go into detail there. It's very fluvial geomorphic here. So overall, a network of rivers exists out of many more smaller rivers than larger rivers, right? Makes sense. It's a dendritic network structure. And hence, we're always going to think that the beaver builds more and smaller rivers, but that might also be a residual of the fact that there are more smaller rivers, right, than larger rivers. So there's a few biases when we do this, when we model those beaver dam extensions and controls on that we have to consider. But that's just as a caveat, basically. So what we did is we used an approach that is very similar to species distribution models in several steps. So this is work by Matt Dennis, actually, was just published. And we went from the data coming from the Swiss government, created models and predicted the distribution of beaver dams actually in Switzerland. And most importantly, we also have a very strong topographic component in that, but I'm going to talk about this a little later. And what we found by, we ran a random forest model and GLM on all of these variables that we thought would be important for beaver dam distribution. And what we found, and this is very good news and different to what other people have found before, is that it's all dependent on physical characteristics of the landscape, which of course lets the geomorphologist and hydrologist in me the heartbeat faster, right? But it's also much, much easier to transfer this approach onto other landscapes, because this is data that we can actually readily get from, for example, digital elevation models. So we found that the beaver dam distribution depends on channel width, channel gradient, minimum channel gradient, stream power, very important, and terrain slope. So, and these were the main factors that controlled where beavers built, which is very good news. We did the ground truthing, of course, like also very much together with the CSCF, with Christoph Angst very much, who knows Switzerland like his back pocket, I think, at least the beaver locations in Switzerland. And then we, our outputs are very, very promising. It seemed to have all worked really well, okay? We could clarify some in the beaver world, heavily discussed thresholds, okay, like channel width. I don't want to talk about too much about this, but this is what people talk a lot about in this world, or the stream power component, for example. So I think we've made Matt, actually, who wrote most of this paper, has made a significant contribution to this beaver discussions. And we came up with a spatially explicit model of beaver dam flooding in Switzerland. So this is where potentially the beaver could dam and flood the surrounding floodplains, right? And this is the outcome. So we would have overall, there would be no people, only beavers, right? We would be able to have 45,000 hectares of beaver floodplains and 9,800 kilometers of dammable river channels. And the big important thing of this is for the management that it's all spatially explicit. So it's embedded in the VCF, this is called in Switzerland. So the management platform of the cantons to be able to manage their landscape, yeah. And this data set is in there. This means that they know now where beavers could potentially flood their houses, or let's be not too negative, the fields, the agricultural fields. So this is done. But we wanted to know in this project what the effects of the beaver are, not only where they would be able to dam, but what would be the effects if they would dam, right? So I already said that there is impact on water quality of the beaver dams. So it's unclear if there's only one or several beaver dams. You know, there's many variables that could control the impact of water quality. And the literature said it should be, for example, denitrification should be a a potential effect of a beaver reach with many beaver dams, right? And we had it was actually a big project. So in 2021 and 22, 313 volunteers surveyed 7,000 kilometers of Swiss River project. Yeah, they took samples at 165 beaver reaches, yeah, in summer and in winter. And these samples were then shipped to the EAWAC, and they analyzed for water quality, which was a massive coordination project that was mainly done by the CSCF. Yeah. This was citizen science, had its challenges in itself. We also mapped then all the data that we got in terms of water chemistry to the distance of the beaver reach, slope, pond volume, water residence time. We calculated the discharge, dam age, number of dams, catchment land use, and local land use. Yeah. So what you do, but the data is still thoroughly confusing. Okay. So at the end, this is the only graph I'm going to show because that's how far the analysis went. We see the effects are variable, right? But good news is, if you look at number 1, okay, here that we have a decrease in nitrate in the surface water at a significant amount in summer and in winter of the sites, but there are many sites where nitrate also increases, for example, in the surface water from between upstream and downstream of a beaver reach. That always is. So this is how much I can say now about this. So in the future, hopefully this is going to be a bit more, we're going to understand more about the drivers. But what I can say, and from this data set, and that is where my geomorphological heart is really engaged, right, is then in 25 of those beaver wetlands, that was 165 sites, I think. And of those 25 sites, in 25 sites, the beaver is allowed to put water on the floodplain, right? All the others sites, the beaver sits within an incised channel and creates ponds. Yeah, but the flooding is only happening in 25 sites throughout Switzerland because of land use conflicts and management problems, people basically. Yeah, and at 14 of those 25 sites, yeah, we had a very good hydrogeomorphological connection between the beaver wetland that it creates and the channel water. And in all of those sites, we got a coherent effect of reduced nitrate in the surface water. So from my perspective, what we find is that the hydrological connectivity, hydrogeomorphic connectivity between the wetland and the river is what drives the positive water quality effect of the beaver. Then we work together with Anita Risch's working group, Valentin and Leonardo. He can't be here, but that is part of his work. And we found that we have a very interesting and quite coherent trend in dissolved organic carbon in the water, which increases quite coherently from upstream to downstream. So now this video was supposed to work, but it did not before. So I'm going to go out quickly out of the presentation. So stay with me. I hope this is going to work now, but you don't see anything, right? Oop. How do I share this now? Can I share the? No, you can't. I can't share that now. That screen with the or not.
I'm trying to put it like this, like a maximize to see if I can. No, it doesn't work like
Yeah, for some reason. No, wait. Ta-da! Magic. Thank you very much. So, because I thought this is maybe the best way of introducing you, yeah, it's 2 minutes, to what comes next in the next part of the presentation. So this is a flight also from Christoph Angst, who I mentioned a few times, very important collaborator for me on this. He flies the drone from upstream to downstream. This is what is Matal in Beaver Pond or Beaver Swamp. So you see, right, that we have on the right side the old channel, right, where originally the water flew very straight and nice. Here in the top part of the pond, already quite some grassland terrestrial processes working. Then as we go in the middle part of the pond now, we see we have much more water on the surface. Yeah, we go now, we reach now the beaver hut. Okay, hut, yeah, it's called in English. They're in the middle, that I think you see it, right? So he's going to zoom into this. You see it's in winter, yeah, in summer that is all totally overgrown, but you see how variable the surface water areas are, right? And you see also that originally the main flow path was on the right, but now the main flow path actually goes on that floodplain, yeah, and continues. And now you go in the lower pond area where the water flows not anymore in the channel on the right, but over the floodplain, right, until it hits the road and it goes back into the main channel. Yeah, and here it's open water surface also in summer. Okay, so you see how the flow path, the hydrology in the system changes from upstream to downstream. This was the main message of this, and also to show you how beautiful it is, of course. Yeah, that was this. Oh. Wait, what?
You want to have your notes?
Ah, yeah, that would be nice. Yeah, it's without notes, but I think I can handle. Super, thank you. Sorry for this, for some reason didn't work before. So in this Martalen beaver pond, what you just saw before, we also embarked, and I called it towards a carbon budget of the beaver meadow, because we wanted to know the entire carbon budget, not just a part. We want, because the discussion in the beaver world goes around, if there's a lot of methane emissions, for example, from this pond, then beavers would not be, for example, storing carbon or creating an efficient carbon sequestration in the wetland. So this is why we wanted to construct a real carbon budget, like, and considering all the fluxes. Lots of work, yeah. So we monitored all sorts of things. I don't want to go into detail, that would take too long. We reconstructed, of course, also the hydrology, like all the fluxes that go in and out the system. So we took approach, we monitored upstream, downstream rating curves, you know. Lots of hydrological work connected. We found that the hydrology is very complex, that evaporation losses are really high, and we have clear signs of disconnected wetland in parts, and in parts high connectivity hydrologically. So water just flows from upstream to downstream without any obstacles. But in parts, the water stays around, it lingers, the residence time increases, which you see, this is a fluorescence test here on that side of that small bulk, right? So most of the water flows through, that's the peak. And the little bulk over here indicates that there's some water that stays around for longer, disconnected, right? And that's probably where all the water quality impact happens. It's partially in German still. This is just a reconstruction of how the flow paths go to let you understand how the disconnectivity happens in the system and how connected it is in parts and how it's not connected in other parts. We have lots of seasonal dynamics. Okay, the vegetation explodes in summer, like typical wetland processes, and dies in winter. And when we then quantified all the seasonal, the yearly carbon fluxes, we found that most of the time, the wetland is actually a net sink of carbon. In summer, however, the area is often also a net carbon source, only considering water and atmospheric fluxes here. However, and it's also very important to note that the DIC, the dissolved inorganic carbon, actually plays a large role. They are not just the dissolved organic carbon, which we mostly focus when we do carbon budgets on. So this was the seasonal, so the water atmospheric fluxes that we investigated. And then we went on to quantifying the biomass in the system. We use drones. We have Dracula drone service, right? We did estimation of dead wood on a decadal. That's more decadal biomass storage than the seasonal biomass from drone images, which you just saw before. And what we also used are old, almost historic, right? Comes from 2008. It's not really historic, but like a set of several LiDAR scans, which gives us enormous amount of detailed information on biomass change over time. And then what we also did is we cored, okay, lots of drilling and more drilling. And then we did more drilling. And it is a very wet location, right? And based on all of these samples and monitoring or surveying that we did, we came up with the sediment depth volume that was created by the beaver, okay? We know now how much sediment is stored due to the beaver in the system. And then we analyzed the carbon in it. Oh, yeah. And so we created this, yeah, it's a carbon budget, okay, which is a boring list of numbers, which always frustrates me when I have to present it, but it's so much work, and everything that we did enters into this one list, okay, the table, yeah. And overall, when I sum this up, is that we had, we made a mass balance of all of this, right? The atmospheric, the water fluxes of what comes in, what goes out, the atmospheric fluxes, and then also the soil fluxes and not fluxes, the soil storage and the biomass storage at the end. And miraculously, it's almost impossible, yeah, it matched. So which means we have a net carbon sink because we store so much sediment and so much carbon in the soil, even though from time to time, atmospherically, the wetland becomes a source in summer. But overall, we have a carbon sink, and quite a significant one, of about 60 tons of carbon per year that is stored in the system. So now roughly equivalent to the annual emission of 137 cars. Okay, if you want to express it like that, the cars will have to be driven about 10,000 kilometers a year. So that is what we managed to reconstruct. What we also found in terms of the carbon pools, we had a look at this as well, because we quantified the carbon. We used a method that is called rocky wall. It comes from geology, like I think oil exploration actually. And we found that the carbon moves in the beaver pond as older it gets into stable carbon pools. So it's really sequestered. And that worked beautifully. We also, yeah, so in a nutshell, carbon is being sequestered in the beaver pond, right? And yeah, so I don't think I have to explain here much more. Overall, when we quantified that and we compared it also to other in Germany, to some beaver matters that we investigated, is that we have an approximate increase always from about 50% in carbon when we compare it to pre-beaver or to other locations in a catchment where there are no beavers. So this seems to be quite a coherent number, 50% about of increase in soil carbon storage due to the beaver. So now what we want to do though, as a final goal, right, is we want to quantify all of this in terms of ecosystem services, right? For this now, this is a summary, right? What we got was we have the spatial extent of the potential beaver impact. We have also a conflict with land use that was already analyzed, I didn't present. We have an increase of DOC, which I presented from Leonardo Capitani. We have carbon storage increase, which we quantified. We have a water balance, so water residence time estimation, and the carbon flux dynamic in the water. And we have some sort of data set that we don't know yet what to do with, which is the nutrient dynamics and the hydrogeomorphic connectivity that we still need to investigate. And in terms of eco, it would be absolutely fascinating now to know what the role is of the beaver in terms of biodiversity. And that is a part of why I give this presentation today, because I discussed that in length yesterday with Valentin, in order to also come up with what the benefits are of the beaver, Swiss-wide and spatially explicit in terms of biodiversity increase, right? So this is the approach. So we want to use all of this data set now together to quantify the ecosystem services of the beaver in Switzerland. But we haven't yet done it. So keep in 1 year, 2 years, or in the future, hopefully we are going to make it. So I've talked at length, over 30 minutes, about the beaver, right? But we can do all of this also for other animals. So we had a project, for example, on burrowing animals in Chile along a climate gradient, which was also absolutely fascinating, but that's just at the side. So now, I promised, though, to talk about the sedimentary ancient DNA. So I hope you understand a little bit better what I've done in the past, right? So I'm trying to understand the feedback, the processes of the animals that they trigger in the ecosystem. So now, based on this, I can go back to the past and basically see if that species was present in the past, and then better understand the ecosystems before human impact, when those ecosystem engineers were still present and available. And they are not the beavers, not the only one. There's many of those ecosystem engineering species. So this is what I'm trying to do in the future. So I'm going to investigate the changes over time and then try to give advice to restoration projects to say, okay, this is actually what would be natural here. That are the ecosystem engineers that we need to reintroduce, for example. And I'm going to do this, so I present some pilot data here based on sedimentary ancient DNA, which is a method where you just basically take the soil and you sequence it for all sorts of animals that you're interested in, yeah? And it has been successfully used in the past in permafrost soils, lake sediments, cave sediments, archaeological contexts, and marine sediments. In rivers, not, and that is for a reason. Because a river is more complex. Now, we don't know where that DNA comes from that we sample, right? When we go and we dig a hole and we do our chronostratigraphic analysis, we don't know, does the DNA come from the catchment? Does it come from a local source? Where does it come from? And that's the work we still need to do because sedimentary ancient DNA is very new. And now we have to basically validate and do this type of work. And we started doing it. This is a site in Germany where I've worked on, the 3 different sites actually, and I started all this work in 2018 actually together with Christoph Spergesen, who is in the room and looks at this now. And and we were starting to do this a few years ago and always at the side project. And now finally, we've got some data from those 3 rivers in Germany where we reconstructed based on sedimentary ancient DNA. And also some botanical macroremnants that we took as a reference, if it's at all realistic what we find in those in that sedimentary ancient DNA record. And we found it worked beautifully. Yeah. So first of all, there's enough data available. This is a heat map. Okay, you can see all these taxa at the bottom that we found in those 3 rivers. So there's on the right side, you see the names of the 3 rivers, the control. And on the bottom, you can see all the taxa that we found. The yellow ones are the ones that we found with the method that we usually use, okay? And all the other are new, okay? We had no chance before we used sedimentary ancient DNA to get on top of all these taxa that was there in the past ecosystem. And that's what we're going to do in the future. And what you see here, just looking at it, lots of trees, right? But you can, for example, see in that area here, which is what we're at the moment looking very carefully at, is here you can see these are all the grasses and sedges. You see how in the oldest river, this is the Vesta 2, it's 3,000 years old, this is 2,000 years old, this is roughly 1,000 years old. It's also a gradient of human impact from the bottom to the top. I can see already how the heat map, just eyeballing it, how the grasses, right, where the system probably lightens up, less and less trees, and becomes more open in time. So that is just an eyeballing interpretation, but it is basically a massive breakthrough, yeah, if we manage to validate the record. And this is, I think I explained that before, we need to validate it because we don't know exactly where the DNA comes from. It might be catchment derived or it might be local. And we have a different problem also with rivers that we don't have in lakes. We use a different type of techniques because of shotgun sequencing, because you can see already in the profile how much vegetation grows on these profiles. And there's a very high risk that we do not sequence ancient, but we sequence present DNA from all this vegetation. That's not the same in marine sediments, for example, or in lake sediments. And so we have to use shotgun sequencing, because in shotgun sequencing, we can separate ancient from modern DNA using those smile plots. Yeah, that's just as an explanation. Yeah, and that's what we're going to do in the next 5 years. I just got a grant for this, and I'm very much looking forward. And to potentially not only dream about natural streams, to actually know what they were all about in the past. And so I want to thank you, the audience, but also the fact that this is a massive team effort. None of this would have been ever done without any of my colleagues. So, and I want to thank them specifically. So that was it. Thank you very much.
Thank you very much. Very interesting talk. Before I take any questions, I just want to push that we had a TV Nano SRF was filming us in the field, and they did a very interesting reportage about all the beaver projects in Switzerland and also abroad. And this was on the 11th of November, so it's quite recent. If you want to know more about our projects, check it out. Is there any questions?
Thanks a lot for the talk and ambitious projects. I had a question about the species distribution modeling of beavers along the river streams. You showed different predictors for the beaver models. Have you made any analysis of variable importance?
Of what?
Variable importance, or yeah, the importance of each variable. Maybe the channel width would have a 30% importance, yeah, and lower for others, and it could indicate a beaver preference.
Yeah, yeah. So we did this, and most important. So the most important variable was slope. So this was, and then it's followed by all the others, right? But it is mainly slope. So the beaver really has a sweet spot where it wants to dam depending on the gradient of the river. So how much inclination there is. If it's too steep, it doesn't do it. And if it's too flat, the river is very large. And that's, I think, the meaning of this. And then it also doesn't do it.
Thanks.
So, I mean, natural hydrology, presumably you can quantify nicely from your models, but like hiking around Switzerland, sometimes you feel like they've turned the water off or on. And maybe that's more in the highlands, yeah, and not so much where beavers are, so it's not so relevant, but somehow the management of water for electricity can be really maybe not so easy to predict.
Oh yeah, that's a very good point.
Complicated?
Yeah, yeah. So the good news about this model is that it's probably based, because it's based on my idea and the availability of data, but it's very much based on geomorphology. So it's very much a DEM-based approach, which means the human effect is very strong. Actually, the biggest one I would almost say is incision of rivers. So all the rivers are incised in Switzerland, almost all of them. Basically, they made them deeper, which means we have a disconnection between floodplain and channel surface, which means it makes it much harder for the beaver to actually put the water on the surface. And I think there is more the problem between, can we, we think is this really a natural potential distribution or not, right? That's where we have more the problems, I think. But because it's a geomorphic model, and we run different scenarios in terms of beaver dam height, we have that under control more or less, because it doesn't depend that much on hydrology. But of course, the hydrology is the reason why the geomorphology is there. So it's inherent in the whole analysis. But I understand your question. It's always going to be an approximation, but because it's such a large data set, you have to, also when you want to manage, we always say that to the managers as well, when you use this model and you want to manage based on this model, you have to go to the specific location and manage based on what we found there. This is just a potential, an estimation of a potential, nothing more. Yeah. So it has its caveats.
Thank you, Annegret, for a great talk. I just wanted to show that 25 of the 165 systems, they had lower nitrogen or nitrate output downstreams than what came in on top. But isn't this just a question of the scale? Because of all the flooding, the nitrate just goes out in the fields and the beaver only distributed over a larger space? Or is it that somehow in the system it gets used more?
I think the latter, because we so most of the systems are incised, right? So most of the system are actually pond systems, not like Matalen. Right now I showed the beautiful pictures. I should probably also have to show a movie of like a cascadic system. And we always sampled upstream of a beaver reach and downstream of a beaver reach. And let's say we have 1,000 meters in between maximum. Mostly it's 200 meters or something that those beaver cascades are long in terms of river length, the beaver reach, we call it. And I think the connection with the floodplain, you mean, right, is in most of the system very limited. So because they are mostly cascadic, I'd say there's something in that system that need to increase, decrease, do something with the nitrate. Yeah, so I think it's mainly within that cascadic systems, not in the interaction with the outside of this, because it's only 200 to 1,000 meters, you know, length. That could well be, that could cause the confusion, of course. You know, if you have input or a point source, for example, let's say drainage coming in or something, that would of course mess up your entire site, right? In terms of investment, we don't know that. So.
Thanks a lot. Yeah, really nice talk. I really enjoyed it. Yeah, I had a question. I mean, I really like your carbon budgets, and I wanted to ask a little bit. Do you have an idea about the mechanism behind? I mean, this carbon thing that you found. Is it? I mean, can you explain it, or how do you explain it? Or do you have any ideas, or why is it? I would have expected actually to be also more. To have a lot of methane actually outputs from this sediment.
Yeah, that's funny, because the methane is so small that we cannot even put it on the graph. We had to express it in kilograms because it's so little methane emissions. But we looked at the ebullition, so this was not a measurement problem. Let's say like this just has very small methane emissions. So the reason why it's such a big source is because of the soil. That's because of all the soil current that we did, and the system acts as at the moment as like a sediment storage area, like this one. So you see the sediment depth, how deep that is. This is like it's variable, but it's in the upper part, 90 to 100 centimeters, so up to 1 meter of soil that system has stored additionally to what was there before. So it grew, the surface grew, right, up to 1 meter in terms since 2008. So, and all this sediment holds a lot of carbon because it's a wetland, right? And that is what makes it a sink. If it would be just the water and you don't quantify the sediment storage, it becomes a source.
So it's kind of like, stored carbon, not being really used.
Exactly. It's being put away, and it's in a stable carbon pool. That is what maybe I didn't express that very well. It's in a stable carbon pool, which we found with using Rocky Wall. So it's actually sequestered. Yeah. So it's being put away, and it's going to stay there. Yeah. For I don't know which time scale, probably thousands of years time scale, millennia.
Very interesting. Thank you.
Just to comment on this further, this is exactly what I do, right? What I love doing. But it, of course, this pond is going to fill up. right? And then it's going to be filled up. Then it's not going to have the same effects anymore because it can't grow the surface, you know, into a into a house, right, or something, you know. So it's going to this massive effect of 60 tons carbon per year is, of course, limited to the point where it is going to be filled up.
Thank you for the nice presentation. I also have a question about this carbon thing. And I know this is mostly Leonardo's part, but you're saying that the DOC in the water is increasing with the
yeah, upstream to downstream.
And are you seeing that as a positive thing?
Yeah.
And why?
We consider it positive because it's supposed to be the source of the bottom side of the food chain, right? So DOC increase means you have more food for all the macrozoobentos, which are eaten by the fish, which are eaten by the, you know, so it's supposed to foster aquatic life. This is why increase in DOC is generally considered positive until you talk about, I think, drinking water. And then sometimes the DOC becomes too high, and that's then a problem for drinking water, but that's not in the range of what we have here. Yeah.
So it's more like pushing like biodiversity up or something like that.
It's supposed to be like the source of all the aquatic life. Yeah, but I'm also now ecologist, but this is why hydrologists investigate DOC. Where is this actually? Yeah.
More questions? Otherwise, I have a question. Is there any ways that this ancient DNA is linking up with the beaver?
Yeah, well, this is originally where it came from, but we didn't manage to find the beaver. So at these sites that I just showed at the end, which is a pilot study, is one point. This one. So this is the sites that we investigated, and in these sites we have beaver gnawed wood. So we know the beaver was there, right? We even have a beaver dam in one of those sites, right? It's very complicated stratigraphy that I show here, but you know, we investigated it very detailed, chronostratigraphically. We dated the sediment so that we know how old it is. All these things were going on. And we found a beaver dam, okay, and beaver gnawed wood. That's why we selected the sites at the first place, but we didn't find the beaver DNA. So spoiler, not all of the ecosystem engineers, of course, are producing apparently enough DNA in the system so that we can find it back. Yeah. So for that, there are techniques, so how you can tackle that. You can sequence deeper, for example. We also used the technique that is called capture, but this is for the future. Yeah. So we are going to try to have, because shotgun sequencing is, for example, less sensitive to rare species than metabarcoding, but we need to use shotgun sequences, not metabarcoding, because of the contamination issues. So we try to circumvent that by using capture techniques. But this we need to develop further, and that's why that's what we're going to do in the future to exactly tackle that problem. You've hit the nail, Valentin. You found the problem.
Just an understanding question. When you showed this distribution model of the possible dam, I mean, I saw in Ticino in the southern, where the rivers are quite torrential. I mean, they are quite, and also regulated by dam. I mean, how can you imagine when the dam release water, either because they need electricity or because there is too much water, can realistically beaver survive in this very
torrential?
I mean, the landscape you show, I mean, it seems like the river are very slowly and quiet and there. I mean, but it was full of red spots.
Here, you mean this?
Yeah.
Oh, it's not there anymore. Oh, no, wait, I have to.
It's like a,
Whoop.
also potentially.
Like this, you mean?
Yeah.
Yeah. Yeah. So that's a very good question. What you see here, but it's so hard to display this on a map like this, you know. So what we see here also in the more torrential or in the higher slope areas, there are always small rivers, right, that feed into the bigger rivers that are they have a too high slope for the rivers, for the beaver, so they don't dam it. What they do dam though are the small rivers flowing into those big rivers. And that's actually that they are almost everywhere. You normally just don't look at them, but you always have those side channels coming in. Yeah, but on a map like this, you don't know which type of river it is. Is it the big one or is it the small one? No? That's why it's so hard to display here. But it's mainly the first to fourth order streams that they dam. Everything that is above is apparently almost impossible for them in terms of slope. So that is the most important variable there. So the high torrential, well observed, the slope is too high, they don't dam. So they're excluded from the model. It works actually quite well, surprisingly well.
So then faster flowing streams still have beavers, right?
Yeah.
But they don't have much of an ecosystem impact other than felling trees, or
yeah.
Is there an ecosystem impact? I mean, do they make little pools or somehow still change the hydrology to provide microhabitats, or is it so small that it's not worth considering compared to the damming ecosystem service, ecosystem change?
Yeah, so the damming ecosystem change is of course the largest, but they have smaller impact also in larger rivers. So for example, in the Netherlands, you know, you have this massive floodplains, massive rivers. Of course, they're not going to dam them, yeah. But what they do is they live on the floodplains and they dam like side waters, brooks, or this, and they live in the bigger ponds that are there, and they of course change the vegetation to a distinct degree depending on what is there, right? So they have an impact. They probably create much more diversity, right? Because they cut vegetation here, create a grassy area here, so they create a more patchy environment. Also, when they don't dam. Unfortunately, they also borrow, right? That's what the Dutch are very worried about, because they actually borrow into, that's where most of the problems come from. If the river is deep enough and the pond is deep enough, what they do is, in order to build a hut, right, they don't construct it in a floodplain, they actually borrow into the banks. And that can then cause a lot of problems. If you think about dikes, you know, water safety measures along rivers, that is a very big problem for the Dutch. Here in the Netherlands, the problem comes from the fact that when you drive through the plateau landscape of Switzerland, you have a river, right, that is incised nicely straight. Yeah? And then problematically, you have a road straight next to it on one side and on the other side too, mostly, right? So the problem is that when the beaver digs into the banks of the river, it always digs underneath the road. And also when it floods, it has to flood the road first to actually access the floodplain. And that is where most of the problems come from. So the borrowing and the channelizing, they also dig these nice little channels along. So they also have some sort of microhabitat impact. You know, they could use a bigger habitat diversity, but small when you compare it to the dam construction. I think everybody's hungry.
Yes. Well then,
thank you very much for the question, the discussion.
Thank you very much, Annegret.